You can see my mouse.
Yes, I can, sir. Hopefully Judy can as well.
Hello to everyone, and welcome to this session. I'd like to welcome you to the session for the plenary session on aeroacoustics, and it's dedicated to John Fox Williams. I want to let you know that this session is being recorded, and I would like all folks to turn off their video and to stay on mute until we allow, at the end of the presentation, we allow for questions. I am Judy Gallman. I'm a session chair, and Doug Nark is the co-chair of the session. He is also the technical chair for the Aeroacoustics Conference, and I'm going to take this opportunity to thank him for his hard work in organizing this conference. Today's talk is titled Challenges and Opportunities for Low Noise Electric Aircraft. Our authors are Ken Brentner, Eric Greenwood, Robert Rowe, and Ted Gann. I would like to take an opportunity to introduce all these authors, and then I will turn it over to Ken Brentner for the lecture. Ken is an AIAA Associate Fellow and Professor in Aerospace Engineering at Penn State. Prior to Penn State, Ken was a Senior Research Engineer at NASA Langley. He earned a PhD from the University of Cambridge under the supervision of John Fox Williams and was mentored by Ferry Farisat. He earned his MS from the Joint Institute for Advancement of Flight Sciences, go GIAS, and a BS from Purdue. A fun fact about Ken, he grew up on a small farm in Iowa, and the first engineer he ever met was an acoustics engineer working to reduce noise on John Deere tractors. Eric Greenwood is an AIAA senior member and an assistant professor in aerospace engineering at Penn State. Like Ken, Eric was a researcher at NASA Langley prior to joining the faculty at Penn State. Eric earned his master's and PhD from the University of Maryland under the supervision of Fred Schmitz, and a BS from the Rochester Institute of Technology. Fun fact about Eric, he is a co-founder of Harmony Aeronautics and is working to build the world's quietest personal air vehicle for the Boeing Go Fly Prize. Good luck, Eric. Robert Rowe is an AIAA student member and is working toward his PhD in eVTOL with Eric. Rob has MS and BS in aerospace engineering from the University of Michigan. Rob is an expert programmer and a self-proclaimed computer geek. Ted Gann is a student member of a graduate research assistant at Penn State, and he is working in UAM and eVTOL noise modeling. He will get his master's degree this month. Congratulations, Ted. And he has a BS in aerospace engineering from Carleton University. Ted is a Canadian, and he takes his work very seriously, and he will start his PhD this fall. And good luck, Ted. With that, I'd like to turn it over to Ken.
Good afternoon, everyone. I wish I could see you in person, but I'm happy you're here. I want to especially give Eric Greenwood and Rob Rao and Ted Gann, they really helped me out a lot on this presentation. It would have been very difficult, if not impossible, to do without them. And I'll try to point out some of their individual work along the way. So first of all, I want to tell you a little bit about this lecture. First of all, our perspective is that we've all worked in rotorcraft noise prediction and noise measurements, especially Eric on the measurement side. And the strategy we took for this talk is that it's a general talk to the Aeroacoustics Conference, but it's a technical audience. So the people that work in eVTOL will probably know a lot of this. We want to put it into context for everybody else too. There's only a brief discussion of electric CTOL aircraft, even though we have the title as electric aircraft, and our focus is on distributed electric propulsion and eVTOL. You'll see that. So I do want to reiterate this is dedicated to Sean Fox Williams, who passed away last December. He was my advisor. I want to point out he was the third Aeroacoustics Award winner after Light Hill. and Ribner. And you'll see he was incredibly important contributions for this field. So with that, I want to start out and talk about eVTOL noise and how important is it in this new evolving industry. And so I went through and picked a couple of quotes from industry leaders. I could have picked others. I think most of the leaders in the industry would agree. But for example, Jobin Bevirt, founder and CEO of Joby Aviation, he said that when he founded it, that the electric propulsion was going to be transformational in that we could build aircraft that were incredibly quiet. So even from the beginning, he was wanting to do quiet aircraft. And then Ian Villa, CEO of Whisper Aero and former head of strategy at Uber Elevate, he has a recent comment saying it became abundantly clear that noise matters most, I put the emphasis, to cracking the code of everyday flight with people and things. So Ian and Mark Moore have founded Whisper Aero to focus on that. So now, in way of outline of the talk, so I'm going to start by an introduction, and I'm going to show an incomplete timeline. I'm sorry if I missed your aircraft or missed your contribution. I had to pare it down, but I want to make some observations about eVTOL noise after that. Then I'll review propeller noise history. I'll look at the challenges, opportunities of the different noise sources and prediction tools. Talk a little bit about the future from our perspective, and then have a conclusion slide. So I started out with this talk thinking about a timeline of electric aircraft. What's the history been? When did they really start? And I'm going to focus on the emergence of eVTOL. And from this chart, you can already see it starts back in 1918 as the first aircraft, first electric aircraft. And goes through, and there's an explosion from 2011. So I'm going to review these milestones. Of course, you can't see these right here. So the first electric aircraft was quite interesting to me. This is the correct picture for the PK-Z1. Theodore von Karman was there. This is the first electric aircraft. It was an observation to replace balloons. It was able to lift 3 men, and it was a quadcopter, four-bladed rotors. And here you can see them. I don't think it ever flew very high, but it flew 4 times. It had a 190 horsepower motor, and eventually that motor burned up. They were trying to make it light. So it's kind of cool to me. The first electric aircraft was a quadcopter. Now, it was quite a long time before any progress in electric aircraft was made. But in 1973, and I'm not going to try to pronounce these names, so I'll just call it the MB-E1. This is a full-size manned aircraft, solely electric power, nickel cadmium batteries at the time. It could fly up to 12 minutes, and in 2017 it was restored. Again, it's quite a long time before much else happened. It went, so next thing was 2008 at Oshkosh. The Electroflyer C flew. In the post, I noted that it was titled Quietly Wows the Oshkosh Crowd. This was an electric aircraft, had a battery that could be charged in as little as 2 hours, flew 70 miles an hour, up to 2 hours. So that was quite an achievement with this aircraft. But then I want to focus in on the last decade. This is where really things start picking up. And you know, there's going to be things happening. And remember that companies were starting to be found, like Joby and Zero and those companies just a little bit before 2011, what I'm showing here. So I want to look at these in more detail. So really, I would say Augusta Westland's Project Zero in June of 2011 was quite important. It was a hybrid tilt rotor lift fanned aircraft. And it was to demonstrate the technology. It wasn't intended to really fly, but it did hover. And it's the first electric tilt rotor aircraft. So this is Very cool looking, an important milestone to make people start thinking about this. And then another, I think, very major milestone was in 2011, the Green Flight Challenge. Now, it was sponsored by Google Cafe Challenge, and the requirements were for an aircraft to fly 200 miles in less than 2 hours, nonstop, and to use less than the equivalent of 1 gallon of fuel, so less energy. And there were a couple of aircraft successful in it, but the first place winner was Pipistrel Taurus Langland LLC. Now, this is Jack Langland, one of my colleagues at Penn State. And it would be a Penn State aircraft, except Penn State didn't want to do the liability. So he formed his own company to do this. But quite an achievement for this aircraft, and really was looking forward. 403.5 passenger miles per gallon. They put 2 gliders together. So then, as we go on, just a few weeks later, in the Volocopter, first manned flight of a multi-copter. You've probably all seen this picture. Quite impressive. Just to start, I love the exercise or Pilates ball for cushion. Then just a few months later than that, Zero had the first flight of their proof of concept vehicle here. Zero's Elon Crew of Stanford's company. This aircraft transitioned in 2014, and this was what eventually led to the Cora, Kitty Hawk. And I know that they were using sophisticated tools even for noise back then. So just as a reference point, I thought was interesting is in the UAS, the small UAS drone world, the DJI Phantom, which is quite famous, was the first consumer drone. That only happened in January of 2013. So that's not even been 10 years. Then later that year, towards the end of the year, the first indoor flight of the Volocopter V200, which we recognize. It was flown inside. It transitioned in February 2014 and can do 60 miles an hour up with vertical takeoff and landing. Now, it's a few years later, Joby was testing their subscale prototype. Of course, no one knew about this at the time. Joby's released that later, but here you can see it, and it's appropriately dark because they were very tight-lipped about what they were doing. Same time period, Hong was flying their 184 with passengers. This is the 184 has the 4 arms on it, so 8 rotors. And then in 2016, almost a year later, a milestone, I think, was the Uber Elevate white paper. That Uber started really, I'll call it evangelizing. Mark Moore, I would consider an evangelist, a strong technical person, and that was an important milestone for the whole industry in this movement. So then Lilium enters the stage. They've been working on stuff, and they had their first flight of their Eagle prototype. It's a smaller aircraft, starting to demonstrate their ducted fan idea. And then in that time period, Kitty Hawk, Cora, which proceeded from Zero, was in flight testing, I think in California, but mostly in New Zealand. And nobody knew about it. Then across the pond in England, the Vertical Aerospace was flying their first prototype of a ducted rotor system. And lots of activity starting up here in 2018. Vahana had its first flight. The Moog, or it was Workhorse, the Surefly had its first flight. And then I put in another conventional aircraft I think is significant, was the first flight of the Pipistrel Alpha Electro. So this was a 2-seater trainer, providing low cost. I think this is quite interesting that it recovers 13% of the energy on every approach, so it could sustain the flight time. Then in June of 2018, Beta Technologies flew their first demonstrator, the AVA-XC. The EHang 216 with the 8 rotor or 8 arms, 16 rotors. It can travel 8.8 kilometers on a single trip, it says. And then also was in beginning of 2019, the Aurora Flight Sciences PAV, personal air or passenger air vehicle, I forget. Boeing bought them. Then Lilium had a 5-seater that they tested in 2019. First all 36 ducted fans. It was tested untethered. Kitty Hawk Heaviside, so they've got a new vehicle that came out in 2019. They have over 237 successful transitions, 100 miles on a single charge, 180 miles per hour. Quite an efficient aircraft. Again, they were working towards low noise and claim 38 decibels in flight. Then as we move on, I'm trying to go a little bit quickly, but Pipistrel Velis Electro looks very much like the Alpha. It was the first electric powered aircraft to receive type certification. 2-seater, again, intended for pilot training. And then I've put down here, because Joby was the first, they received US Air Force airworthiness approval as part of Agility Prime. But Beta in May of this year, lift aircraft with their Hexa vehicle and Kitty Hawk Heaviside have all achieved this certification. And so that brings us up to the present. I've included on here this Aeroacoustics conference today. So what do we learn from that? Well, electric motors eliminate noise, but that wasn't really the problem. So just having electric motors is not good enough. Propellers are back, and lots of them. So we know how to make low noise propellers, but there's some performance trade-offs. And let's be clear, propellers in edgewise flight are like helicopter rotors, or perhaps even worse, because if they don't have cyclic pitch, there's more unbalanced loading. So we have to take that into consideration. And the other observation I would say is there sure are a lot of different configurations. I've shown a variety, but there's more than that. And so there's many opportunities for strong aerodynamic interactions, which is a challenge for us. So now I want to talk about propeller noise and rotor noise just a little bit to sort of orient people that are not from a propeller rotor noise background. So this is a taxonomy we've sort of adapted from Tom Brooks and Schlinker's paper. I just want to note Tom Brooks right now. We'll be talking about the Brooks-Marklean method, and Tom just recently passed away in the past few weeks, so I'd like to honor him as well. He was a giant in the field. But anyway, we have thickness, loading, and high-speed impulsive noise. For helicopters, this is not going to be an issue, or should not be an issue for eVTOL aircraft. Most of the noise is going to be loading noise. We still have deterministic and non-deterministic. And we break it down into unsteady, there's steady for low harmonic loading, unsteady, narrowband, broadband for propellers, and broadband noise. Typically, we think of helicopters. We have these sources. I'll talk more in detail about most of them. So the governing equation that's really applicable and widely used is the Fox-Williams-Hawkins equation. Now, it's a rearrangement of the Navier-Stokes equations following Lighthill. So we have a wave operator operating on acoustic pressure or density with three source terms. The quadrupole term is that of Lighthill's acoustic analogy. And this is an extension of the most general form of Lighthill's acoustic analogy. Now, this monopole term in mathematical form represents the thickness noise, the fact that fluid's being displaced. The loading or dipole term here is there's force vectors acting on the surface, and they're accelerating even in steady hover, whether it's on the blade, it's steady, they're still accelerating because they're rotating. Now, I want to point out this loading source term also includes unsteady, non-deterministic sources, so broadband noise can be modeled by this term. And then we have the quadrupole term, which accounts for nonlinear propagation effects, non-uniform speed of sound, any actual sources like turbulence outside of the surface of the body, and we'll talk about that a little bit later. So we usually use Farasat's formulation 1A, and this will be the major equation in the paper. I've highlighted different colored terms, because I don't want you to worry about the full equation. We have velocity and Mach number terms. These have to do only with the motion of the blade. So you can see the thickness noise only depends on those, and the distance, the R, distance to the observer. In the loading term here, we have these green terms, which are the loading vector, and they are the loading on the blades. And I'll point out there's a time derivative of loading. So we need time derivative of loading and motion. And we get these things from external codes or theory or approximations. And of course, the accuracy of the inputs are important for the acoustics accuracy. Now, the rotor environment for these vehicles is very complex, maybe more complex than helicopters, really it is. So if we have a lift plus cruise type of configuration here, you can see we have rotor strut interaction or empennage or wing wakes going into a propeller. We can have rotors close together that might interact with each other. In this Bahana-like configuration, we have tilt rotors and wings. In fact, you know, the propeller is going to have an interaction with the wing. It's going to cause unsteady airflow, so it's going to actually scatter the noise from the propellers, but also this unsteady loading is going to cause the wing to be a radiator too, potentially. And we can have rotor airframe interaction. So we've got lots of potential interactions we have to deal with. Also, just like helicopters, we can have axial flight. For a helicopter, this would be hover, but if we have propellers, it just means axial flight. And the velocity distribution is the same all the way around the propeller. It's essentially steady loading on the rotor blade. But in edgewise flight, as we've drawn here, we have higher speeds on the advancing side of the rotor, lower speeds, a reverse flow region. For eVTOL with low tip speeds and forward flight, this could be a very high advance ratio in a large region that is in reverse flow. Now that'll result in noise directivities, and we've just used a propeller here. In edgewise flight, just like a helicopter, we could have thickness and high speed impulsive noise primarily in front of the vehicle. With low tip speeds, we could probably get some behind too, because Doppler amplification won't be as important. Broadband and loading noise rated primarily above and below the rotors, but if we get blade vortex interaction, we get highly directional directivity from that interaction. But in axial flight, loading and broadband noise are going to be the dominant terms for us, and they can occur both above and below, or in front and behind the rotor, and in the plane, especially since these blades tend to be twisted more than helicopter rotors. Blade vortex interaction occurs in edgewise flight, typically when the rotor is at an angle of about 6 degrees from the rotor plane in descent, often, and we'll get highly directional noise. This is still important. We have to care about it on descent, especially in these aircraft. Now, when we get BVI noise, here is the acoustic pressure versus time, non-dimensionalized. And you can see it occurs on both the retreating side and advancing side. The character is a bit different typically, but we get these really impulsive spikes. And you can see those in the acoustic spectrum. This is a non-dimensional frequency. These are harmonics, and the higher harmonics are due to BVI. And we can even get higher ones when we get into broadband noise sources. So BVI is important. It can be very annoying, but we can have other interactions that do something similar. So for example, in this recent test just published It was in the 40 by 80. Stevenson led that, but there's a lot of other players that you'll recognize here. I'm showing the case for a full wing, but they did a no wing, which is this rather sinusoidal type of noise. Then with the half wing, so it would stop in the middle, and the full wing, and you see quite a different higher amplitude and more harmonics involved, almost impulsive. And you can see if we look at the spectrum for those cases with the same kind of color coding, the basic aircraft is blue, and you see that it falls off very quickly. By the fourth harmonic, it's quite low, but the BVI, or the interference noise, stays quite high, and it will continue for more harmonics. Another type of a similar interaction would be a counter-rotating coaxial rotor. Here was a test done by this team, I think Eric was associated with. They varied the rotor spacing, so they're separate rotor systems. And what you see here that's, I think, important is that the tonal noise increases quite dramatically as the rotors get close together. So you can see when we're going from 2 rotor radii separation to 0.25, we have an increase of more than 14 dB in the tonal noise. But the broadband noise is different. The broadband noise actually increases in this particular case as you get farther apart. So this total signal is a combination of the broadband noise and the tonal noise at different separation distances. So there's probably a minimum here that you can achieve. So let's look more focused at this broadband, this non-deterministic part that we just introduced in that last figure. For propeller noise, if we go back to what's in Harvey Hubbard's book by Maglione, Hansen, and Amiet, they describe it as periodic, narrowband, random, and broadband noise. So these are really harmonic noise. This noise, narrowband random, is not quite periodic. It really is tonal in nature with a spread around the tones due to turbulence and other factors. And then we have the random noise. We really have all the frequencies involved. That's why we call it broadband noise. Now for self-noise sources, this is from the famous Brooks, Pope, Marcolini RP. They describe several types: turbulent boundary layer trailing edge noise, and it changes with angle of attack where you have separation and then stall. Of course, that depends on the thrust level. If you have laminar flow, laminar boundary layer vortex shedding noise, blunt trailing edge noise, and tip noise. So all these sources are important. Here, this is from Brooks or Burley and Brooks paper, where the red line is the sum of the prediction. You have all these different sources put together, and the black line is the prediction or the measurement. So you need all those sources. And in fact, I've included BWI, or they included it. It's quite an important source that we're going to have to deal with. It fills in part of the spectrum, but the other sources matter too. Now, the blade-wake interaction is like blade-vortex interaction. It's related to the vortices, but it has to do with the turbulent field sort of entrapped or carried along by the tip vortices. And often it's in a more perpendicular orientation than for parallel BVI. So this wake turbulence and inboard turbulence all gives another type of noise source we have to pay attention to. I think it's especially important for eVTOL. And here, taking different people's results and sort of merging in one figure, we have a BVI kind of event and a BWI. These are acoustic pressure versus non-dimensional time. And you can see this is more of a broadband, random kind of signal on top of the BVI signal. And here are the directivities, but you can, this chart showed that, well, self-noise is sort of important in climb, strong, steep climb. BWI is more important and other climb that's more benign and what we'll probably be flying at. And then when we get into descent, the BVI and loading noise are most important. And this has to do with the forward speed. So Eric Greenwood ran a calculation setting up sort of a nominal, what we think might be an eVTOL rotor. And we wanted to show that, in fact, if you look at the overall sound pressure level versus tip Mach number, and these tip Mach numbers tend to be on the low side for helicopters, maybe a bit high for UAS, what happens is the thickness noise falls off very quickly at this in-plane observer. The loading noise a little bit more slowly, and the broadband noise actually tends to increase with lowering of tip Mach number. So you really have some sweet spot, depending on the configuration on the rotor, where you'll be in a bucket between broadband noise and discrete frequency noise. So that's something to consider. And I think we're going to find out that this is also the range where eVTOL wants to operate, and then the current vehicles that are coming out are operating. So let's talk about some of the challenges and opportunities. And I'm thinking again from a noise prediction, but I want to look at the sources. So broadband noise, Fox-Williams and Hawkins, Fox-Williams' contribution to that paper isn't the only one of about the same time frame within the same year. Fox-Williams and Hall was really the first paper on trailing edge noise. They had a semi-infinite plate and used a Green's function approach. AMI a bit later used a bit different approach and had the first influence of finite chord and used the surface pressure distributions. Howe used the Green's function approach like Fox-Williams, but alternating governing equation, and Howe had probably the first review paper talking about the different broadband trailing edge noise papers. These are theoretical formulations, but Brooks, Pope, Marcolini, and several others focused on semi-empirical methods, and this was probably the dominant one. There's based upon Fox-Williams and Hall's theory, but then they used empirical measurements that they took, a very extensive series from a 0012 airfoil. Now, very recently, and something we used in this presentation was a review article by Sung-Kyu Lee and other esteemed authors in Progress of Aerospace Sciences this year. This is a good, if you're interested in trailing edge noise, you really should review this. But the idea is you get a U to the fifth kind of directive or power law for broadband trailing edge noise, which is means it's higher than U to the sixth, which would be the surface sources, cardioid shape, and that's reproduced by several methods. And the challenge here is that we have noise generated by turbulence, and turbulence going past the boundary. So this is hard to predict. We need empirical methods often to do it. So just a little bit more about Brooks, Pope, and Marcolini, their RP. There was a physically based, they based their results on similarity spectra on all these NACA airfoil tests they did in the Quiet Flow Facility at Langley. And this has been used widely for helicopters, UAM, and I should have put wind turbines on here. It's been extensively used and then modified for wind turbine use. Takes the steady flow conditions, and they get out a 1/3 octave sound pressure level. So for rotors, it's a blade element approach. Each element has noise generated on the blade, and there's some incoherently. And it's been implemented in many tools. I'll just mention a few: NASA's BART code, RotorNet before it, I think, and NASA's AA-2, a SNFM, which I think is due to come out. It's in use at NASA, I believe. NREL has their FAST code for wind turbines, in which they use a modified version of Brooks, Pope, Marcolini. It's in PSU op-op, it's in lots of different tools, and it's been advanced. So the challenge is, will this be good enough? I mean, we're using it, we're relying on it, but is it good enough? And one of the things I think that says that, yes, it will be very useful, and we have been finding it useful, is that if we look at, it's been demonstrated for UAS to be quite good, surprisingly, because this is right small and low Reynolds numbers. This is tip Mach number versus chord Reynolds number. We've used it extensively for helicopters, where it's very helpful and probably the best method we have there. higher tip Mach numbers and higher Reynolds numbers, and then wind turbines, lower tip Mach numbers, but very high Reynolds numbers. And the UAM, we believe, fits right in here with these Reynolds numbers and tip Mach numbers. So that's right in the middle of this. So it gives us good reason that scaling should work fine. Here's an example of how we can also improve BPM. In this case, by Pettingill and Zawodny a couple of years ago, they used the rotor net, which used a uniform inflow model, and then into BPM, and they got all the different noise sources. In this case, which was a high thrust case, the separation noise was really important. It's quite good, but it misses it a little bit right here. If you 5 to 6 dB, I would say. But then they used CAMRAD2 to get a better inflow using a free weight. And you can see, boy, they really got this case matched quite well. So improved inputs really can improve the predictions, but this is a semi-empirical model. So if you improve just parts of it, you might not always get better improvement. That needs to be carefully studied in each case. The other opportunity with trailing edge noise is that we can have passive noise reduction through things like serrations. Here are different serrations, porosity. These are foam. Serrations can reduce the span-wise correlation and hence the noise. Porosity can help if you have blunt trailing edges or delay vortex shedding. It can stabilize the flow and destroy span-wise coherence. Then you can use things like combs. So we have passive devices that we could possibly use. I haven't seen much about this so far. People may have been working on this, but I know in helicopters at Penn State, Mark Mulmer's worked on developing airfoils for laminar flow on helicopter rotors. What if we could do laminar flow rotors for eVTOL in the various configurations? That would help potentially reduce our turbulent boundary layer noise. The other thing is the more physics we understand, the better we can predict and also then develop quieter vehicles and rotors. So for example, like AMIA using wall pressure spectrum models where you're modeling really the loading rather than the noise directly. Lee has done that in their UC Davis quiet fly code. I'm going to talk more about high fidelity CFD, CA, and lattice Boltzmann. That's another way to approach this, where we have more physics. Another thing I want to talk about, challenges and opportunities, are aircraft noise prediction. And really, when I say aircraft noise prediction, I'm really thinking that this implies full vehicle flight simulation. We need to think about a flight simulation, which means we do the flight dynamics of the vehicle and the aerodynamics computed together. We need, if it's real time, a pilot or a pilot model to describe how the vehicle will likely fly. We need a model of the control system, because the control system and the control system gains can be very important about the noise. This is something you get when you're doing a flight simulation and you're flying this, especially real time. It needs to be time accurate. It doesn't have to be real time for us to learn what the real aircraft is going to be like. And our simulation will predict the rotor loading, airframe loading, and we can compute the interactions with that. And then we can do the time varying noise sources and their directivity. So this is quite important. In helicopters, we've been doing this recently with a code PSU Helisim, which is flight simulation, and then CHARM rotor module, a couple of PSU op-op. And this was an example from Mrinali Botra's PhD dissertation for a Bell 407. This is a 6-degree descent. We did the flight test is the blue line. There's sort of nominal conditions. It was supposed to be flying at 0 degrees roll, a certain pitch angle, a certain yaw, 0 degrees yaw. But in actual flight, it doesn't follow that exactly. Even the velocity is not quite steady on the descent. So we actually try to simulate that with our pilot model to get as close to the flight test as we could. It didn't quite match it here. I think this is not the best Mrinali did. But what you can see, here's the flight test. This is sound exposure level on the ground. Then there was the simulated flight and the nominal flight. And the simulated and nominal probably bracket the flight test. That neither one are quite right, but you can see even with these rather small variations, we get a substantial difference in the noise prediction. So we really need to account for that. So we're working on that at Penn State on a new system we call a distributed electric propulsion aircraft noise prediction system. We call it DEPSIM, and the flight simulation is PSU DEPSIM. For distributed electric motors, it has to handle electric motors. It has to handle lots of rotors and other control surfaces and ways to control the aircraft. It's a non-unique trim. And then we take the high resolution out from CHARM loading and put that into PSU op along with the rotor kinetics, and we predict the noise. So I'll show you examples from that in a little bit. But one of the things important with UAM is we have non-unique noise, non-unique trim of the aircraft because we have many different rotors. We have interactional aerodynamics. They can be flown lots of ways, and we have non-unique control. It's over actuated. So we can have continuously varying RPM that can be used for control, in fact, or variable pitch for control, other control surfaces. And we think most UAM noise analysis probably focus on one when we have a steady condition and look at the geometry. But an opportunity is asking the question, what control strategies can we use to minimize noise? And certainly we've done this with tilt rotors in the past. For an example, in our forum paper this year, we said, well, let's look at a DEP, a lift plus cruise configuration. And we can have two thrust schemes. We can use variable RPM for each of the rotors or variable collective pitch. And we're going to look at a simple maneuver. It's in low speed flight. It's a controlled doublet. Let's look at the roll doublet. We're going to roll about 5 degrees in one direction for 4 seconds, go back 5 degrees the other direction. And we're going to do that with variable pitch and variable RPM with our PSU DEPSIM coupled system. Now, you can see both methods give us essentially the same flight profile for this roll doublet. Now here, this is just our first case of trying to look at this kind of thing. But if we look here, well, here is the variable RPM, here is the variable collective pitch. This is the case for variable RPM, and I want to focus your attention on the blue and black dashed lines. These are both in the plane of the rotor, in front and in back. And you can see during the maneuver, we have quite a big change in the loading noise. And you can see these spikes from the initiation of the start of the roll, the stop, and again the starting of it the other direction and the stop. And we see that in both cases. Out of plane, the difference is not so big, but for this variable collective, in this case, we see smaller variations in noise, especially out of plane, using this control procedure. So this is a first look at this. Now we think human perception of eVTOL noise is very important too, and there's a lot more I could have included, but I wanted to put this in here. For helicopters, John Leverton and Pike and then later Vandenberg and others have pointed out that there's non-acoustic factors can be quite important. John called it virtual noise. So the helicopter noise perception depends on things like safety. Do people believe this aircraft is safe? If they don't, they'll rate it as noisy. Are they worried about their privacy? Are they worried about people flying over and invading their privacy? If so, they'll complain about noise. And if they think the economic importance isn't, if it's just rich people flying over their homes, then it's noisy. If it's going off to the oil rigs with their husbands and sons working, then it's considered less noisy. They have the same type of perception issues for wind turbines. If they're getting, if it's economically important or people care about the green, they're less noisy, but the visual appeal can be people say it's ugly, they'll say it's also noisy, or they have shadows going across them. So they have these perception issues that aren't directly noise related influence the perception of noise. In UAM, I think we have the same kind of things. The perception of safety is going to be one. If people think that ducted fans are safer than open rotors, lifting rotors, then they might perceive it as quieter for the same levels. Visual appeal, we think UAMs, and I think manufacturers agree, should look good, and if they look good, they'll probably be considered more quiet. Another thing is they should not sound like helicopters. So this is a negative association trigger. It's readily identifiable if it's a helicopter sound. And sound quality, although I thought this was a gimmick at first, I think it really matters. If the sound doesn't sound like a helicopter or a drone, that's important. And the manufacturers now are saying the same thing. So I wanted to include this chart from Steve Rizzi's internoise talk from NASA Langley. He's coined the terminology, I think he coined it the perception influence design process of UAM noise. And I'm a believer that this is what we really need to do. We need to model the noise. We need to, in an MDO environment, try to optimize the whole aircraft, including the noise. We make a normalization of that, get a human response and feed it back. And ultimately that needs to inform the design process to make quiet vehicles. And this will be ongoing. I think this is important in the future. An example, this is for a UAS, how listening can be important. So this is a test where they measured car noise and small UAS or drone noise. You can see the sound exposure level on the bottom and A-weighted sound exposure level, then the annoyance on the axis here. And generally, the black is UAS, the drone, the blue is the car. And if you look at it, it's about a 5.5 to 5.6 dB penalty for drones. They're considered noisier at the same level. So levels alone don't capture perception. For example, variable rotor speed could be an issue. It can be used for primary control, not only in UAS, but UAM, some vehicles. Some studies have shown that continuous variation in RPM may affect the noise levels. That seems obvious, and especially if it's rapid changes, perhaps. But it also changes the perception of the noise. You have a time variation in the noise that you can see in spectrograms. And RPM change, we found in our recent paper, probably doesn't change much over one rotor period for UAM sized vehicle with larger rotors. This introduces the idea, can we model some of this as quasi-steady? It would certainly give us a prediction speed advantage. So we should accept, one opportunity is to look at this more in the future. Can we assume a periodic? The variation remains almost constant over a period. It's still periodic. It could be used for fast predictions, but it won't fully account for interactions. So then moving on, I just don't have time to talk about the other things more. I want to talk about high fidelity simulations. They have an important role as we go forward and a big opportunity in my mind. So why would we want to use high fidelity? Well, we need to do it to capture the unsteady loading, especially in interactions. And we need to do it, we think it's important for broadband, non-deterministic noise. So we needed to capture unsteady boundary layers, blade-wake interaction, other kinds of interactions. And these are challenging. They really require cutting-edge CFD techniques like large eddy simulation, detached eddy simulation. LES has really been increasing in adoption over the past 5 years. We want to use that here. Another alternative, I would say, is lattice-Boltzmann methods. We've seen results for UAMs using lattice-Boltzmann, certainly with PowerFlow and other tools. So how good are we now with the current CFD-based approaches? Well, here's an example from a few years ago for a quadcopter sort of a model. Uses PSU WAP for the Fox-Williams-Hawking solver and Helios for the CFD. And you can see they can model this with and without the body around the aircraft for rotors. And they're getting some interesting noise. We don't know how good it compares because we don't have an experiment for this. But you can see differences with and without the body. So I don't know if this image is going to play well for you, but I want to point out this is another big calculation with the Helios overflow tool chain. You can see lots of turbulence going on. Even in the boundary layer on the trailing edges, you see unsteady flow happening and acoustic scattering and shielding going on. You see how the air loads from the wake interact with the body here. All these things are important, but we're probably not capturing all the details we need for broadband noise. So a question is, where did direct computational acoustics go when we think about these vehicles? And by that, we mean sort of CFD-like, but high resolution to capture the acoustics too. Well, long propagation distances are very expensive. That's something we still can't do. The other thing is things like nonlinear disturbance equations require a coupled simulation of bulk flow and acoustics. And in my experience, these have been a little bit disappointing. And another thing is we need these type of methods when we have very strong flow acoustic interactions, especially like jets, high-speed jets, and other things. We don't think that that's probably needed for eVTOL, and we think that we have to watch that, but that's a reason we can decouple and use hybrid methods. So the CFD2 acoustics, what I've just shown a little bit, this is the most common where we use the pressure, the loading vectors or pressure on the surface when the quadrupole or the off-body terms have the minimal impact. But permeable surface is still something people are working with. We can capture the volumetric corrections or noise sources, and includes nonlinear flow effects or non-uniform flow effects where the acoustics has to propagate through it, at least in the region. So I picked one example of this by Spillart and his co-workers. They used a permeable surface on a body. In this case, it had like a landing gear. And they used both permeable and the solid surfaces, and they found that there was shielding. So if you look at this micro, here's this small region where there's a cavity. They looked at this microphone 0.5, and the green is with the permeable surface and the red is the solid surface, both Fox-Williams-Hawkins. And they compare it, because this is close and it's in the CFD domain, they can compare it with the CFD. And the permeable matches pretty well until you get to higher frequencies. But the solid surface doesn't. Now, when it's on the same side, so at this observer 0.14, well, the permeable still matches better, but they both match pretty well because the shielding is not so important. And we also know, and I've used this, I did work like this, other people have done it, but Len Lopes and his colleagues worked on this problem with a vortex ring going inside a permeable surface to outside. It shouldn't really generate noise inside the volume when it's inside, nor when it's outside, but as it passes through, since they neglected the quadrupole term, there's noise. And so these are different time segments. This is a cross-section of the acoustic pressure inside the volume. You can see it's nearly zero here, but as the vortex gets closer to the surface, in these 3 time steps here, you see higher levels. As it goes outside at 7.7, it gets lower, and then it goes back to something nearly zero. So this spurious signals are a problem with this. People have tried and have some success, but I don't think we've fully solved that problem yet. Then an alternative method that we've seen used, I think has import here, is the lattice bolts method. Now, I don't want to go into all the details of it, but they use a different governing equation. They calculate, they have a collision operator that they use. They have various states, and it actually has particle distributions only travel in characteristic directions. So as opposed to traditional Navier-Stokes, each state can be captured by purely local operations. So what does that do for us? Why would we use this? Well, the nonlinearities are local. The non-local operations are linear. So it's simple to implement, easy to parallelize, and well suited for GPU computing, we think, and it scales out to massively parallel quite well. It has no numerical dissipation, low dispersion, and we know those things are important for acoustics, and it can generate both the generation of sound and the propagation of those acoustic waves. So here's an example for the DJI Phantom 3 rotor. This was a power flow. I think this is up here, Thurman et al. So you can see the experimental results are in red and the power flow here. This is in plane, this is out of plane, and it's even better out of plane. At the highest frequencies, it doesn't agree as well. And what they found with the grid refinement study was that as they improve the grid resolution, they're able to capture the higher frequencies better and better. So here's another example of lattice-Boltzmann. This is actually kind of a cute example. I think it really shows what we'd like to be able to do. Damiano Cassiano presented this a couple of years ago at the Aeroacoustics Conference in Delft. Here they did a scattering over a city block for a eVTOL vehicle in hover. They did 80 revolutions. It was about a little less than 3.4 physical seconds of time. And this took 250,000 CPU hours. They probably had a lot of CPUs to do this. If you have 10,000 CPUs, it'd be 25 hours of wall clock time. But this is what we'd like to be able to do, and we probably need to be able to do in urban environments like this. So now I'd like to wrap up. This is a brief view of what we think should go forward in the future, some opportunities and challenges together. Let's see, okay. Well, we think low noise design tools are very important, like our PSU DepSim coupled system with PSU WAP-WAP. We do need to improve, and we want to continue to improve broadband noise models, pressure spectrum modeling, like UCD. It was QuietFi and other models probably are good, but we also need mixed fidelity models. So low fidelity for wake transport we think would be good, with a near body solver to handle the wake interactions. That way we think we can reduce the computational domain of CFDs with hybrid methods and use cheap methods far away for propagation and transport, and then high fidelity methods, maybe lattice-Boltzmann in the wake region where interactions are occurring. We also think that not only the vehicles in the future, but the methods themselves need to be acoustically aware for design tools. We want results in minutes, not hours, weeks or days when we do flight simulation. And we probably have to look at variable RPM. Is this important for the noise generation? We've already started to look at it with simple methods, but does this change the broadband noise, for example, due to acceleration effects? We don't think the acceleration is high, but we've got to look at that more. Another new exciting thing is hardware acceleration. I mean, GPUs are very important, but now we have ray tracing and even acoustic modules for noise propagation. We think that these kind of hardware advances we should try to use those for our tools, because they're being used in gaming and other things. And then we proposed and plan to start working to develop hierarchical tools. So our goal is we'd like high fidelity tools to inform lower fidelity tools and essentially provide correction models. We would like to use machine learning to help develop reduced order models, develop corrections. But we also think that the low or mid quality fidelity results should provide feedback to the high fidelity tools. That might be the user saying this was a good result. It might be some automated method to tell we need to have more high fidelity work in here. Our results don't agree very well in this region. Noise measurements is another opportunity we think is exciting, and it's really coming online. We need, of course, noise measurements for validation of tools, certification, community impact. But there are several activities that are about to give us much more noise measurements. We're working at Penn State on several FAA projects. One of them is Project Ascent, Project 27 that Eric is managing, I'm working on. They're measuring noise from Beta's aircraft, in-flight and static measurements. It's done already. We also have a whole series of drones and a reconfigurable drones that we can fly at a local mid-state airport. And they're doing noise testing of these now to help us understand multi-rotor vehicles. Then we're also doing physics-based modeling. We think it's going to be necessary to fill in the gaps. So we need a coupling of the measurements with the prediction tools, because there's so many operational situations. There's so many different vehicle configurations that we can consider. But we also need measurements. I kind of put it as an afterthought here, but for aerodynamics, especially long wake ages, the interactions are important. Finally, we think acoustically aware aircraft are going to be useful in the future and are needed. Effectively, we need noise abatement procedures, but we think that if you can do real-time noise modeling, then the aircraft can become aware of the sound it's outputting at any given time, based upon weather, based on flight conditions, and based upon the importance to the community at that time. So we think these aircraft will adapt their configuration, flight dynamics and controls, and have on-the-fly flight path planning and replanning. But especially the control system needs to be aware in advance of certain things it shouldn't do because it will raise the noise. So I went a little bit over an hour, but just one more slide, the conclusion. I think there's really many challenges for eVTOL, urban air mobility, advanced air mobility, whatever you want to call it. It's viability and acceptance. And I want to put here, even though this is a noise talk, safety always has to be first. We can't do anything that makes the vehicle not safe, and these vehicles won't survive if they're not perceived as safe. And also to the people on the ground. Economic viability, obviously, is very important. These can't survive, they're not economically viable. But then the noise is important. It's right up here with these. The companies recognize that, I think. And the noise has to be different from helicopters or different from drones. And of course, infrastructure is a big challenge too. All of these things are being looked at, but there's a lot more to go. And I think even the second generation of vehicles will have more effect on. Now, the good news is I think the leading developers, the ones that I can get enough information to make some sense of, and there's been recent articles, Sean Captain had a nice article on fastcompany.com where he was able to find the rotor tip speeds are probably between 0.5 and 0.2 for the current vehicles. He estimates the disloading around 12 pounds per square foot, which is right in the range for helicopters, a little bit higher than light helicopters. And Joby and Kitty Hawk are estimated to be in that range. Noise levels, well, they tell you 65 is their target, 55 is what they achieve, 45, 38. How low can you go? But they're talking the right kind of numbers. We've got to characterize what these are like, both en route and probably more importantly on takeoff and transition. And they have been emphasizing sound quality. That's a really nice, Joey just put out this week a really nice video showing the comparison en route noise to airplanes and helicopters. I think you might like to look for that. And the sound quality comes into play there. But new experiments and prediction tools should help us lower the noise even more in future generations. So with that, I will finish the talk, and I'm happy to try to address any questions. If any of my co-authors are on there, especially Eric Greenwood, feel free to jump in too, but I'll try to take the lead on questions.
Ken, there are 2 questions in the chat window.
Okay.
If you'd like, I can read them for you.
Okay, you can read them.
It says UAM and AAM business models require a huge number of flight movements of these novel vehicles in order to work. Is this factor, number of flight events, adequately represented in ongoing noise studies? It seems that noise perception or annoyance due to sheer number of flights is not adequately captured by typical noise discriminators, such as LDEN. What is your opinion on this?
Well, I agree that there are lots of different operations. There's lots of different ways to trim the vehicles, non-unique trim. There's lots of things going on. I think that captures the spirit of the question. And I don't think standard things capture those well. We're going to have a learning process here. And I think at Penn State, Eric and I both would agree that we need prediction tools, a variety of levels to model all the way from actual real-time flight, like in flight simulation, to fill in the gaps between what, you can't measure all these either. There's so many, it's going to be very difficult in experimental campaigns. So we've got to build confidence. We use the high-end prediction tools to validate and strengthen the lower-end ones. We do flight simulation. And then we do the real campaigns with the vehicles. And I think we're going to have to learn about what to use for certification, what other kind of metrics along the way really capture perception. And that's going to be ongoing. That's a challenge, but we can make it into an opportunity maybe. Hope that touches upon the question.
And there's a second question. It's about the addition to aeroacoustics in UAM. What about the vibroacoustics? It's also going to be increased in porting as well, given increased impingement of propeller weight on airframe.
I think that's very important. In fact, I didn't talk about that when I didn't talk about the interior noise problem. I think that also refers to, that's probably a really big challenge. I have no information on what the noise levels and vibration levels are in the aircraft, but you've got lots of rotors close to a very light airframe. And I think that's going to be something we're going to have to look at. But I don't have any specific knowledge, except I know it's going to be a big challenge. The interactional aerodynamics that we need to calculate the noise will also be important to get interior noise. So we'll need to calculate the vibrations. If we can calculate the enough fidelity and detail for noise, we can probably calculate the vibrations. We'll also have the sound levels right at the airframe, where we can talk about transmission losses and things like that. And we'll have to be very innovative, just like they've been designing the vehicles themselves. They'll have to be come up with some great ideas, probably active noise control and headsets and other things will have to be used. And I'm sure they're working on that. And that will probably be the differentiator between different vehicles. Have they approached noise well? Have they thought about vibration controls? I haven't thought about it a lot, but I know it's important.
We have another question asking your opinion on what do you think are more promising in terms of noise signature, open rotors or ducted rotors?
Well, so there's probably 2 kinds of ducted rotors that they may be referring to. The open, like a Bell Nexus configuration, or the original vertical aerospace demonstrator, where they had large rotors that had a shroud around them, I call it, is probably different from, say, the Lilium idea, where you have lots of well, I don't know how high speed they are. They're probably, the tip speeds are not that high, but you've got a lot of fans. I think Lilium and the fans is going to gain some perceptual advantage, because I know when I first showed my wife, and she knows about helicopters, when she saw that, I said, "Oh, that looks very good," because it looks safe to her. And fans are not supposed to be noisy, you know. I don't know how noisy they'll be. We'll have to see. But open rotors are always a challenge. We can make them quieter, but the interaction noise doesn't, like broadband noise, doesn't necessarily go down with tip speed. So there's limits on what we can do. And so for open rotors, I think we have to be very important about configuration. I can tell companies that, you know, when you look at some of the vehicles, you can see they've tried to avoid download on the wing, like a tilt rotor can have. They've tried to, but some of the companies, like the heavy side, you've got the wake of the wing, you've got a sort of a blown flap by having the tractor or a pusher configuration where the rotor tilts with the flap. Looks like it's very aerodynamically efficient and smart. They get lift out of that, but it may not be as good acoustically. So that, you know, the challenges are there, and I think there's probably more challenges for open rotors, but they can have lower disc loading. The fans in the Lilium will have higher disc loading, and if you can really achieve benefit from liners and things, that remains to be seen. So I've kind of rambled on about that now. If anybody wants some more questions about it, I'll try.
Yep, there's two more. One is like an optimization between the number of rotors and the diameter, right? Because some of these vehicles have 4 rotors, 8 rotors, even 16. Of course, you've got different rotor diameter sizes, RPM changes. So where's do you think the sweet spot is?
Well, I don't know where that is, frankly, and I think I think we have a lot of challenges like that. I think we need to look for sweet spots. The companies, you know, I think we're seeing a little bit of convergence in what companies are showing us, and what you know, especially like the I'll call them maybe a little later to the table, where they have designs but no, you know, maybe prototypes that they use in a display floor but not a flying vehicle. I see things like tilt rotors, like the vertical aerospace new vehicle looks a lot like Archer's vehicle, looks a lot like other vehicles. But I don't think we know yet if even configurations are going to, which settle out into preferred configurations. And then in those configurations, how many rotors? The one thing I can see is, you know, Joby, the first thing we saw from them, kind of, they had a lot of propellers on it, more like the Maxwell. But now the vehicle they're flying has less. I suspect they've done their trade studies and they've looked at that, and I suspect it's they have to do all the things. Noise is only part of it. They've got to get the performance, the stability and control, ride quality eventually, all those things. So it's a challenge. I don't have an answer for that question, other than I think with the tools we have, we'll be able to start investigating that more.
I think we can sneak in one more question. And this is about the importance of psychoacoustics when you're talking about RPM controlled vehicles. I guess like when you can vary RPM across the different props that you have.
Yes, so I think one of the things that has been noted even in helicopters is that the broadband noise can be modulated around the blade passage period. And that has people at Langley, Andy Christensen and his colleagues and Steve Rizzi, They have these spectrograms, and they show some correlation that does affect perception. So clearly, with variable RPMs, that also will have an impact on perception. We need to watch it, but I think in addition, we need to be paying more attention to just the modulation, even if we have a constant RPM of broadband noise. And we're actually looking at that at Penn State. Other people have looked at that a little too. I know that Sun-Kyu Lee, I think, looked at some of that, and we need to look more about that. The modulation, from our experience and little experience we have with looking at a man-sized vehicle and then, flying it with a flight simulation with different trim procedures, we don't think that we're going to have a large change in RPM per rotor period for larger vehicles like you might have in drones. But, there may be advantages to not having minimizing the modulation. There may be advantages to having different RPM for all the rotors and making a more broadband-like signal. So I think we'll have to be clever. And I think the companies have been trying to do this. I don't know the details of what they've done. So I hope that addresses it. But psychoacoustics is very important, I think, in this process. And we really need, like Langley and Steve Rizzi and his group are doing, predicting that, letting people hear it, and maybe a jury or otherwise, and giving feedback to the design. I think that's critical.
We're out of time for questions. I'd like to thank Ken for this very interesting talk. I really enjoyed it, and I'm sure others have also. There were lots of compliments along with the questions. So thank you all very much. And Ken, special thank you to you and your group and your co-authors.
Yep, thanks everyone. Appreciate the help of my co-authors.